Hello students, in today's class we will try to understand about the working of polarizers. So a polarizer is an optical device that is used to convert an unpolarized light into a plain polarized light. A polarizer will have a particular axis called transmission axis, and this polarizer will allow only those components of electric field that are parallel to this transmission axis to pass through it. So you can see here we have an unpolarized light. This has electric field in all possible directions perpendicular to the direction of propagation of the wave. So this is going along this direction here. So as it passes through this polarizer cuts out all the electric field components that are perpendicular to the direction of this transmission axis. And what we have as the output is a plain polarized light whose plane of polarization is exactly aligned to this transmission axis. The same polarizer can be used as an analyzer when we use this same mechanism to detect whether the incoming light is plane polarized or not. So here you can see we are again using an analyzer. In this situation it is called as analyzer to check whether the incoming ray is polarized or not. Now what can we use to make this polarizer? So usually certain crystals or prisms like nickel prism or materials in which the transmission axis is aligned, such as in Polaroid sheets. So these are often used as polarizer. So inside these crystals and inside a Polaroid sheet, we will have specific axis called transmission axis, and only the electric field components that are parallel to the transmission axis will be able to pass through this polarizer. So as a result, we will be able to produce linearly polarized light through this method. Now here you can see another representation. So this is an unpolarized light. Here we have a polarizer whose transmission axis is in this direction, and the output light will be plane polarized, and the plane of polarization, as you can see, it is parallel to the transmission axis. This is because only those electric field components that are parallel to the transmission axis actually pass through this polarizer. And again we can use another analyzer to check whether this incident ray is polarized or not. So when we come to this analyzer, this actually obeys Malus law when it transmits a light ray. So let us study Malus law. So according to Malus law, if we have a plane polarized light whose plane of polarization is defined, and then when it passes through an analyzer whose transmission axis is aligned at an angle theta with that of this plane of polarization, then the intensity of the transmitted light and the intensity of the incident ray are related as I equal to I1 cos square theta. So here I1 is the intensity of this incident plane polarized light, and I is the intensity of the output ray. Theta is the angle between the transmission axis and the plane of polarization of the incident ray. Now let us try to understand about this Malus law and the reason why they follow this relation. So in order to understand that, we must consider the electric field and its components. So here in this picture, you can see a plane polarized light whose plane of polarization is along this particular direction, and it is getting incident on this analyzer. So we are talking about the Malus law, and when this plane polarized light hits on this analyzer, it will be split into its components. A component which is parallel to the transmission axis, and a component which is perpendicular to the transmission axis. So that will happen naturally, and the transmission axis will only allow the component which is parallel to the transmission axis to pass through. So as you can see, if E0 or say E1 is the electric field of the incident ray, which is plane polarized, then it will be splitted into Ex and Ey. Here Ey is the component that is parallel to the transmission axis, and only Ey will be able to pass through this analyzer. Here theta is the angle between the plane of polarization of the incident ray, which is this direction, and the direction of the transmission axis. So you can find that if E1 is the electric field, magnitude of the electric field of the incident plane polarized light, then this Ey is of course is E1 cos theta, because you can see this is the theta angle, and the component that is adjacent to this theta angle is E1 cos theta, and this Ex is E1 sin theta. The transmission axis will cut out this Ex components and will only allow the E1 cos theta components to pass through. E1 is the electric field of the incident plane polarized light. So you can see it here. This is the plane polarized light. Its intensity is I1. So this is the analyzer. The analyzer is aligned with its transmission axis at an angle theta with the incident plane polarized light. And as we have stated, the Malus law is that I is equal to I1 cos square theta. Now let E1 be the magnitude of the electric field of this incident ray. Then we can split it into two components. One is E1 cos theta and the other one is E1 sin theta. And the analyzer will be cutting out this E1 sin theta components, and E1 cos theta components of the electric field will be passing. E1 cos theta component is of course aligned along the direction of the transmission axis, and as a result we have a plane polarized light at the output side again, with its plane of polarization aligned along the direction of the transmission axis and its amplitude equal to E1 cos theta. Because as we have said, only E1 cos theta components of the electric field will be able to pass through. So if E1 cos theta is the magnitude of the electric field, what will be its intensity? We know the intensity is related to amplitude as I is equal to amplitude square. Here electric field is the amplitude. So initially the intensity is related to E1 as I1 is equal to E1 square, because E1 is the magnitude of the electric field. Now here, what will be the intensity of the transmitted ray? It will be I is equal to E1 cos theta the whole square, which is equal to E1 square multiplied by cos square theta. And since E1 square is I1, I can write I1 cos square theta. So this is the Malus law. So Malus law simply considers that the electric field component that is parallel to the transmission axis will be transmitted. And from the knowledge of I proportional to amplitude square, we can in fact deduce Malus law. So this is how intensity is related when the plane polarized light passes through an analyzer. The transmitted light will have a lower intensity I, which is equal to I1 cos square theta. And you must also understand that how this relation comes into existence, and that is simply because of the reason that the amplitude, the electric field is getting splitted up into components, and the parallel component is actually passing through, which is E1 cos theta. Take the square and you will get the Malus law. Now let us write some special case scenarios. So what will happen if theta is equal to 0 degree? That means if the the analyzer has its transmission axis aligned parallel to this plane of incident ray, plane of polarization of the incident ray. So obviously all the electric field components should be able to pass through, right? So let us put the Malus law here. I1 equal to I0 cos square 0. Cos square 0 will be 1. So I1 is equal to I0 itself if theta is equal to 0 degree. Now what will happen if theta is equal to 90 degree? That means if we place this analyzer aligned in such a way that the transmission axis is perpendicular to this plane of polarization, we will have I1 is equal to I0 into cos square 90 degree, which is 0. So I1 is equal to 0. I should have written I0 and I1 here. So we have stated the Malus law like I is equal to I1 cos square theta. So I equal to I1 and I equal to I1 cos square 90. So this is simply I. So let us stick on to this notation. Here I1 is the intensity of the incident plane polarized light and I is the intensity of the transmitted light, which is also plane polarized. We will use I0 intensity for some unpolarized light. So let us stick on to this notation, I and I1. So this same exact scenarios will be repeated when theta is equal to 90 degree and when theta is equal to 180 degree and when theta is equal to 270 degree. When theta is equal to 180 degree, we have the transmission axis again parallel but in an inverted position. Earlier if we aligned transmission axis along this direction, in the case of theta is equal to 180 degree, we will invert this analyzer and keep it like this towards the downside. So again the transmission axis and the plane of polarization of the incident ray will be parallel and we will have I equal to I1 again. The full intensity of the incident ray will be transmitted. Now when theta is equal to 270 degree, we again have the condition of theta equal to 90 degree itself. In the previous case, when theta is equal to 90 degree, this will be the transmission axis alignment, and when theta is equal to 270 degree, we will rotate it back to here, a 180 degree shift between 90 and 270. So they all actually correspond to same scenario where the transmission axis is perpendicular to the plane of polarization of the incident plane polarized light. Again, no light component will be able to pass through the analyzer. So these are some special scenarios relating to Malus law. Now let us try to understand a special case when an unpolarized light is passing through an analyzer or a polarizer. Suppose we have an unpolarized light which has electric field components along a lot of directions. And what would happen to this light when it passed through a polarizer or an analyzer? As I have said, polarizer and analyzer are the same device. Its position in the experimental setup or its use will actually determine whether it is a polarizer or an analyzer. So when an unpolarized light is passing through an analyzer or a polarizer, as we know, there are a lot of electric field components aligned along all theta directions in an unpolarized light. In that circumstance, each of the electric field component will be split up into a parallel component and a perpendicular component. There will also be another electric field. It will also be split into a parallel component to the transmission axis and a perpendicular component to the transmission axis. In fact, there are a lot of electric fields in all possible theta directions along here and here, and each of them will be split into components parallel to the transmission axis and perpendicular to the transmission axis, and each of them will be contributing parallel components with different amplitudes. Like for example, if we have an electric field along this direction here, it will contribute a bigger parallel component, and if we have an electric field along this direction, its parallel component will be very small. This will be the parallel component, because most of the electric field in this case is aligned along the perpendicular direction. So what will be the intensity of the transmitted light? Suppose I0 is the intensity of the incident unpolarized light. What will be the intensity of the transmitted light? I call it as I1, which is the plane polarized light produced by a polarizer. So I1 is equal to I0 into average of all the possible thetas. Since there are a lot of electric field components, suppose E0 is the electric field vector of the incident ray, and there are a lot of E0 vectors along all the directions. So the EY is simply E0 cos theta, and I1 is equal to EY square, because EY will be passing through this polarizer, and I1 is the intensity of the transmitted light. So that is equal to E0 square cos square theta. But we cannot simply state like that. There are a lot of components, and we should consider the average value of this. Average value of E0 cos square theta, contributed by all the electric fields contained in the unpolarized light. So the incident ray which has an intensity of I0, when getting transmitted I1 and I0 will be related like I1 equal to I0 into average of cos square theta, which is the average value contributed by all the electric fields present in the unpolarized light. So let us calculate that. Now I1 equal to I0 into average of cos square theta. So you must know that the average of cos square theta evaluated between all the angles of 0 to 2 pi, it is actually 1 by 2. So you can find it like this. Average of cos square theta is defined as integral 0 to 2 pi cos square theta into 1 by 2 pi d theta. So find this integration value. You can prove that this is equal to 1 by 2 itself. Also, you can simply remember that average of cos square theta over a full cycle, a full wave 0 to 2 pi is 1 by 2. So I1 equal to I0 by 2. So this is how an unpolarized light will behave upon transmission through a polarizer. So let us summarize what we have learned here. When an unpolarized light hits on a polarizer, each of the electric field component will be obeying the Malus law, and as a result, to find the intensity of the transmitted light I1, it will be I0 into average of cos square theta. You take average here since there are a lot of electric fields, and you will have to find out the effect of all the electric fields on the output side. So I1 equal to I0 cos square theta over the full range of 0 to 2 pi. So it is equal to I0 by 2. So if the incident ray has an intensity of I0, upon transmission through a polarizer, it will have an intensity I1. It will be plane polarized with its plane of polarization parallel to the transmission axis, and I1 and I0 are related as I1 equal to I0 by 2. Now when this plane polarized light meets with an analyzer, I1 is its intensity, which is equal to I0 by 2, where I0 is the intensity of the initial unpolarized light. Now if theta is the angle between the plane of polarization of this plane polarized light and the transmission axis of the analyzer, then as per Malus law, I equal to I1 cos square theta. The transmitted light I and the incident ray I1 intensity of the incident ray I1 will be related by the Malus law. And since I1 equal to I0 by 2, this is equal to I0 by 2 cos square theta. So I0 is the intensity of the unpolarized light. It will be cut short to I0 by 2, which is simply I0 into average of cos square theta over the full range of 0 to 2 pi. And this I1 will be again reduced to I as per the Malus law when it passed through the analyzer. So I hope this working of polarizer and Malus law is clear for you. We will try to work out certain problems so that you may understand more. Here you can also see that this theta angle could also be defined as the angle between the transmission axis of the analyzer and that of the polarizer. Here we define theta as the angle between the plane of polarization of the incident plane polarized light and that of the transmission axis light. This was defined as theta. And since this direction of the electric field is parallel to this transmission axis, we can say that this theta also represents the angle between the transmission axis of polarizer and the analyzer. Both are same because this plane polarized light was produced by this polarizer light. So this plane polarized light will have electric field parallel to the transmission axis of the polarizer. So in a way, this theta is also the angle between the transmission axis of the polarizer and the transmission axis of the analyzer. So I hope this working of polarizer and analyzer are clear for you, and the basic concept of the Malus law is clear for you. We also looked into the effect of polarizer on natural light, which is I0 average of cos square theta. Since there are a lot of electric fields, we must take the average, and thus we got I1 equal to I0 by 2. I hope these portions are clear for you. Thank you.